Hey everyone, today we're going to solve question number 4 from the USNCO step by step. So this problem combines electrochemistry with the thermodynamics. So I'm going to start with the part A. Which electrode is the anode and which is the cathode? So we are given a galvanic cell, as you can see, and we have zinc and we have also the lead. And remember this, in any galvanic cell, oxidation occurs at the anode. I'm gonna write this. At the anode we have oxidation, and at the cathode we have reduction. Please remember this. Okay, now we can determine the anode and the cathode without using numerical electrode potentials. So we need only the activity series of the metals. So in the activity series, zinc is above than the lead. That means zinc is more reactive and more easily oxidized. And therefore, our zinc, in this case, will lose electrons and will act as the anode. So something like this will happen. Zinc will lose electrons. This is anode. But lead ions will gain these electrons and will be reduced to the just lead. So they will accept 2 electrons and the lead will be formed. And this is at the cathode. And the final answer is that at the anode we have zinc and at the cathode we have lead. Okay, now we're moving to the next question. Alright, so now we have standard reduction potential for the zinc. And they are asking us what is the standard potential for the lead. So look carefully, the question asks for the potential at 298 kelvins, right? But the problem doesn't give us the potential of the cell directly at 298 kelvins, right? But instead, they give us a graph of the cell potential versus temperature, right? Cell potential versus temperature in the kelvins. So the graph is basically telling us if you want a cell voltage at any temperature, you just need to plug that temperature into the equation instead of X, right? So the graph is needed because it will help us to find the E cell at 298 kelvins. Okay, and now, because we have 2 solutions with the 1 molarity, right? The measured value at 298 kelvins will correspond to the standard E cell. So that means E cell will be just equal to standard E cell. Okay, now we're gonna use the line equation. E will be just equal to 0.77887 minus 0.000515. And instead of X, we're gonna plug our temperature, which is 298 kelvins. And that means our cell, which will be equal to just standard cell, will be equal to 0.635 volts. Okay, now we're gonna use the main electrochemistry relationship. So standard E cell is equal to standard E cell of the cathode minus standard E cell, just the E of the anode. Okay, and from part A, we know that at the anode, we have zinc, and at the cathode, we have lead. Okay, perfect. And now we can rewrite this as a 0.635 potential reduction of the lead 2 plus 2 lead minus E standard zinc 2 plus 2 zinc. Okay, now we have all of these values and we just need to find our potential for the lead. So let me clean this real quick. Okay, so 0.635 0.635 is equal to x. I'm just calling the x the potential of the lead to plus to just lead. So x minus negative 0.762. So this will give us the plus. That means 0.635 is equal to x plus 0.762, and our x will be equal to 0.635 minus 762, and x is equal to negative 0.127 volts. So this is our final answer. Okay, so the graph is essential because it helps us to find the cell potential specifically at 298. That means you also can find the, for example, your cell potential if you want to like find your cell potential at 330, 324. You just need to plug this temperature into the into this equation instead of x, and you will get the cell potential at the temperature you want to find it. Okay, now we're moving to the next question. Quick note, if you want to seriously deepen your understanding of chemistry, check out my website, chempra.academy. There you will find full chemistry courses, challenging practice problems, free resources, my original Olympiad-style questions, and detailed chemistry blog. Everything is organized in one place for students preparing for competitions or advanced exams. Alright, now let's continue. Okay, in this question we need to find our delta G, delta H, and the delta S for the reaction below, this one. Okay, and first of all, we need to understand this. We are given a plot of the cell potential E versus a temperature, and it's a straight line. So this is already in the form of the straight line. So y is equal to b, which is just intercept, plus mx. Our m is the slope, and our m is equal to negative 0.000515. And our b, which is intercept, is equal to 0.3887. Okay, so we just rewrote the thermodynamic relationship into a straight line equation, and that we can read thermodynamics quantities from the slope and the intercept. Okay, now we just need to remember that our delta G for the electrochemistry is equal to negative NFE. So the number n is just the number of electrons that transferred. So in this case, our number of electrons is equal to 2. F, which is Faraday's constant, is equal to 96,500. And E standard, we already found it. It was equal to 0.635 volts. Okay, now, knowing all of this information, we can find our delta G. And our delta G will be just equal to negative 2 multiplying by Faraday's constant, multiplying by the cell potential. And this number is equal to negative 122,555 joules per mole. So, okay, our delta G at 298 kelvins is equal to this number, which is the same as negative 122 kilojoules per mole. Okay, now we need to find our delta H and the delta S, and we're gonna find them, those numbers from the slope and the intercept. So we already know the fundamental thermodynamic identity. So delta G is equal to delta H minus temperature multiplying by delta S. But we also know that delta G is equal to this. So negative NFE is also equal to delta H minus T delta S. Okay, now if we're gonna solve this for the E, standard E, we're gonna divide both sides by negative NF, and we will get that E will be just equal to negative delta H standard over NF plus T delta S and F, right? So from this we can identify what is the slope and what is the intercept. So of course our t is our x in our equation right here, because the temperature is independent variable and we can change our temperature, but these values, delta H and F, delta S, we cannot find, we cannot change them. So our t is just the x in the equation. So let me rewrite this. So from this equation, we can see that our E is just equal to Y. Our negative delta H over NF is just equal to B, which was intercept, plus mx. Our x, as I said before, just our temperature, and our m, which is slope, is equal to delta S over NF. So now we can find our delta H and the delta S from these values, from the intercept and the slope. So if you remember, our intercept was equal to 78.87. So that means intercept is equal to negative delta H over NF, and our delta H is just equal to negative NF multiplying by the intercept. So delta H is equal to negative 2 multiplying by the, for this constant, multiplying by the intercept. And this value is equal to negative 152 kilojoules per mole. Okay, now we are going to find our delta S. So delta S is equal to NF multiplying by the slope. So our slope was equal to negative 0.000515 multiplying by 2 multiplying by the for this constant. So this number is going to be equal to negative 99.4 joules per mole per Kelvin. So yeah, this is our three answers. Our delta H is equal to this number. Our delta S is equal to negative 99.4 joules per mole per Kelvin. And our delta G is equal to negative 122 kilojoules per mole. It's better to write negative 123 kilojoules per mole. Okay, yeah.